Greetings everyone, I am Shubham from MATLAB Helper. In this video, I will discuss the Newton's law of cooling in MATLAB. Let's derive the equation that we will use in our model. Newton's law of cooling states that the rate of temperature change of a body is directly proportional to the difference in temperatures between the body and its surroundings. Let's consider T to be the temperature inside the system at some time t and Ta to be the temperature outside the system. And according to the law, dt by dt is directly proportional to T minus Ta. Here T is the short version of dt. Removing the proportionality sign will get a proportionality constant K known as the cooling constant. You must have observed that the equation we got here is an ordinary differential equation. To solve this ODE, I will use the variable separable method. On separating, integrating and taking exponents, we get the solution of the differential equation Tt equal to T plus C time exponential of K times T. To get the value of C, assume that the initial temperature at time t equal to 0 be T0 and final time temperature at time t equal to F be Tf. Then C is equal to T0 minus Ta, and on applying the value of C in our ODE solution, we will get the equation Tt equal to Ta plus T0 minus Ta exponential of K times T. The solution to this ordinary differential equation describes exponential increase or decrease of temperature difference over time. Now that we have derived the equation, let's move on to the modeling part. Before moving ahead, I would like to highlight that only 5% of our viewers are subscribed to our channel. If you love our work, then show us your support by subscribing to our channel. We will define a function that I will name Newton cooling for the modeling part. I have given 5 arguments to the function, k as the cooling constant, n as the number of time steps, T max as the time interval for simulation, T0 as the initial temperature of the system, and T environment as the temperature of the surrounding environment. The number of time steps n, cooling constant k, and initial temperature T0 will be used in a loop to get the final temperature spread over the simulation time Tmax. In the loop, you will have to iterate through every time step and calculate the final temperature at each time step. You can write the equation that we derived earlier inside the loop. I have also introduced some codes that display the calculated result in the console. For the graph, I am simply using the plot function. It would be best to experiment with the arguments of the plot function to get a nice looking graph. Now that our model is ready, let's run it with some values. Here is the calculated result in console and the graph for this value. Note that the graph shows an exponential decrease in temperature. Let's try it for some other values. We can again see an exponential decreasing graph. You can also try it for the case where the internal temperature is increasing, like this. As you can see, the model works perfectly for increasing temperature as well. The results that we have obtained here verify that our model is working perfectly. If you want to access the MATLAB codes developed by me, visit the blog with the link in the description and purchase the blog resources. Thank you for watching this video. Do like this video if you found it helpful. If you have any queries, post them in the comments or get in touch with us. Follow us on LinkedIn, Facebook and subscribe to our YouTube channel. Education is our future. MATLAB is our feature. Happy MATLABing.